Hello everyone, it's November the 10th. Alright, let's do this. Finally we got back on the difficult track. It's an old problem. Done it before, but I don't remember this at all. There is a directed weighted graph that consists of n nodes numbered from 0 to n minus 1. The edges of the graph are initially represented by the given array. Perfect, I have a given array. And then from to edge cost, meaning that there is an edge from to to with a cost, okay? From, to, and cost. Graph n and edges initializes the object with n nodes and the given edges. Add edge adds an edge to the list of edges where edge is equal to this, okay? It is guaranteed that there is no edge between two nodes before adding this one. Start to ring a bell. Shortest path returns the minimum cost of a path from node 1 to node 2. If no path exists, return minus 1. The cost of the path is the sum of the cost of the edges in the path. Shortest path returns the minimum cost of path from node 1, node 2. If no path exists, return minus 1. The cost of the path is the sum of the cost of the edges. So basically it's like Dijkstra, but things are constantly changing. Yep, it does ring a bell. I definitely do this before, but I don't remember. I don't remember how this one is solved. Do you remember? Shortest path from 3 to 2. Yeah, it's going to be 6. Right, but if we add an edge, shortest is 0 to 3 is minus 1 because there's nothing go to 3. Add edge 1 to 3 with 4. And the shortest from 0 to 3 is going to be 6. How is this solved? Well, we definitely can't run. Well, that I'm not sure. I'm not sure if we can run. There must be restrictions on the newly added edge, right? It is guaranteed that there is no edge between the two nodes before adding this one. Yeah. So, well, it's only 100. I don't think so, though. I seriously doubt it. That we can just Dijkstra every single time. How was this solved? I think the original idea is definitely, yeah, we just Dijkstra, but that's not going to work. Or I don't think that is the intention. Right? It says you're gonna call, yeah, because the edge length is n times n minus 1. That is definitely not the way to go. But then how? Basically, we can say if we add an edge, what will be changed? What will be changed if you add an edge? So you're connecting two nodes together, right? which means any nodes that's starting from the newly added node can have a new, destination. Did I solve this myself last time? I didn't put in nightmare, which means it's not that hard. There's no self loops, no repeated. And you just keep adding edges. Wow, I think I solved by myself last time. When was that? In June. What was it? What was it? Did I just Dijkstra it? I doubt it. It's not gonna be that simple. You just Dijkstra this thing? That's not gonna fly. So yeah, what changed if you add this? Because every time you can only add one edge, right? Therefore, anything that does not go through this node will not be changed. That's not true. That's not true. It doesn't go through this node before because it could have a... And if you add edge before you call shortest path, it's fine. You just add edges. It's okay. And after you add edge, you have to do a first shortest path call. You'll call Dijkstra, right? And in Dijkstra, you will record the... That's not right, because Dijkstra is you set from one start to go to the end. And in this case, you go from any start to any end, right? There's no rule. I know you can run Dijkstra every single time, but do you want to? What was it? A heap. The shortest path. How did I solve last time? I really have no idea. Yeah, shortest path from 3 to 2. You really have to... Yeah, this just... There will be repeated computation. That's what you want to avoid, right? As a hint, I have no clue. You're kidding me. It is. The hint just tells me to do Dijkstra every single time. Really? Come on, man. Come on, man. Seriously? I was trying hard. I tried to find something else for this. I thought we're gonna you wanna Dijkstra this in Java? Well, Dijkstra will have the path. Will have the graph, right? And then how do you do Dijkstra? You have a heap. Well, you need to have a shortest path to reach each one, right? And the heap is the shortest path to reach each one, which means a heap has to contain two things. Yeah, I mean, if that's the case, let's just Java it. I think we can handle this. It'll be fun. Okay, I think it'll be fun. All right, graph. Graph will be. Ugh. It's always going to be adding new stuff, so it's going to be a list of what? A list of array list, but I don't think it's possible to do a list of array list. So we might as well just go list list of integer. So that'll be graph equal to new array list. Okay. So what we're gonna say is for int I equal to 0, I smaller than n, I plus plus, graph dot add new array list. Then for int temp of edges, cost. Dang it, you need cost. That's okay. Int, which means will be a node and a cost. Then what? We say graph dot get temp 0 is from dot add 2. What's 2? 2 is dot add new int temp 1, and the last one's cost, right? Yeah, temp 2. Okay, so that was that. We set up the edges. Then add edge is easy. Basically, we just say graph dot get edge 0 dot add new int edge 1 edge 2. That's it. Shortest path is also not that hard because we're just going to call it a private int Dijkstra. So we have the graph. All we need to know is, node 1. Oh, that is Dijkstra already. We do Dijkstra here. All right, so what do we need? We need a priority queue. Priority queue of int heap new priority queue comparator compare int tuple, right? We're gonna compare based on 0. It's going to be a min heap, so that will be fine. So the smallest will come out. So we have a heap. Then we need to have an int min path, right? New int n. You're like, what the hell is n? That's why we need an n. We'll handle it here. Int, no, this dot n is equal to n. Okay, so we have an n. What else? What else? What else? That's about it. Then we have a start, right? Now I think at the beginning it's all gonna be infinity. Yeah. Should we say for int I equal to 0, I smaller than n, I plus plus. Initially everybody is integer dot max value. That's the initial. All right, and then we'll say main path node 1, because we calculate from node 1 to node 2, right? So node 1 will be 0, and we need to push node 1 into the heap, right? So we say heap dot add new int, gonna be node 1 and also 0, right? The minimum cost to reach node 1, right? The minimum cost to reach node 1. Now we can say while heap is not empty, right? Heap is not empty, we'll pull it out, right? We'll pull it out. Then we just say int temp, it's fine, equal to, now I can do int temp outside. Node cost. Okay. So inside I can say node cost equal to heap dot poll. Okay. Now we have the node, right? The current node, and we have the cost. And then we need to go through the graph, right? We'll go through the graph and say for list int, oh my goodness, children cost of graph.get node cost 0, right? So we go through that. Is that right? Oh, this should be int. My bad. Child cost is a child cost. Okay, so for each child cost, right, I'll use the current cost plus the child cost, right, and then see if it's smaller, right? Then we say if child cost, that's the cost, plus node cost 1, if it's smaller than main path child cost 0, smaller than a child, then main path child cost 0 will equal to these two added together, right? And then heap dot add new int child cost 0 and this thing adding together. We can actually do this because I already pushed this in. Right, we'll add this. we'll add to the heap. And then blah, 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 then we go for the next one. Now, this is if it's not empty, we'll do that. And then we say if node cost, the cost is larger than min path, node cost 0. If that's the case, then we'll continue. That means we encountered a node that hasn't been updated yet. Right? We'll continue. We try it again, try it again, try it again. And we say if it reaches, right? We just say if no cost 0, it's the node, is equal to node 2, right? Then we have reached, then we can break. And we'll return no cost 1. They'll say that you have not been initialized. Actually, that's not true. Actually, I will do this. Return node cost 1, right? And if we go through everything, nothing, then that's gonna be -1. Yeah, we have something returned here. That's okay. All right. So this is basically just, Dijkstra. Nothing special. I want to have one test case anyway. Looks about right. I think that's pretty much the case, right? It's use Dijkstra for each shortest path call. Because it's 100. Oh, what the hell? No. Are you kidding me? Are you kidding me? The second one. How? How is Dijkstra not right? Did we 1, 2, 3, 4, 5, 6, 7? Are we what I'm saying? Are we overflowed? That's the only thing I can think about. Don't think that we will overflow. It doesn't seem to be that big. What the hell is this? I don't even know how to debug this. Did you do Dijkstra wrong? One way to check is to see. I doubt it's gonna. I mean, it's only 10 to the 6. Right? That's only 100, and most 10 to the 7 is not gonna overflow, so it's not an overflow issue. but we did do it wrong. One, two, output is way too big. 1, 2, 3, 4, 5, 6, 7, 6. Did they add edge wrong? From, to, and cost, right? And each time we always set a heap 0, which is, oh, it should be 1, I think, because we're using a cost. Yeah, we're adding cost. Yeah, that's an oversight. Dijkstra is right. So, yeah, that's it. Huh, interesting. I did a little bit more here. Did I use a heap? Yeah, I did. So it's just Dijkstra. Huh. Let's see, it's not if this is larger than, I mean, yeah, but doing this will make things a little bit easier, but that's okay. O n initialization is e plus v. Initialize the list of size v. Add edge is o n. Oh, they also like doing n times. No, I don't want to do that. I just want O1, right? That's OV plus E log V. E log V. Okay, that's the time complexity. E log V. Which means this is O ON. Right? This is ON. This is O1. This is ON, this is O1, and this is O N log V. No, log E. No, it's log OE log V. E is edges, right? OE log V. Yes, it is log V because the heap you're popping those, you put the nodes into it, so it's log V. Why does it matter? Shortest path. The shortest path is 01. Oh, OM. Oh, shortest path is 01. Oh my goodness. What's this again? Floyd-Warshall. It's not the first time I saw this. I've seen this many times. Iterate through all possible intermediate nodes K, source nodes I, and a destination J. For each pair of nodes ij, we update the minimum cost if there is a shorter path through the intermediate node K. In the addEdge method, we address the requirement to add a new edge to the graph. We take the edge information as input. To update the adjacency matrix efficiently, we iterate through all pairs of nodes and check if the path from I to J can be improved by going through the newly added edge. If there needs an improvement, we update the cost accordingly. This is commonly known as the relaxation step. Find the shortest path. That's 01. Yeah, it makes sense, right? Okay, let's see. Graph. So we do a matrix. Everybody filled with the largest. I raised our stream. That for each row. Nah, I will just use. I won't use that. But anyway, okay, that understandable. That's just filled up whatever it is there, and then for I as the nodes to themselves, that I understand, and then from I to J, going through K, right? That's what it means. We go from I to J, going through K. So adjacency matrix from J to K shall be the minimum from I to K. No, J to... Hold a second. Minimum from J to... this is original. And J to I and I to K. We go through an intermediate. That is an interesting thought. We go through an intermediate. It doesn't matter what this intermediate is. Just go through all of them. Because there will be eventually a shortest path being found, right? And in this shortest path, we'll have to go through some intermediate or not, right? Or not. It doesn't really matter. And look at here. K, I and J could be the same, right? If I and J is the same, then no matter what K you find, but we're not looking at I to J, we're looking at J to K. Oh, we using I as intermediate. I have no idea why they do this, but it's the same thing. It's the same thing. Basically, we say if I don't look at this, right? If I just say from I to J, we want to find the minimum, right? and if I to j is connected. But we should also try to find all the others. Right? I to the other, and then this to this. Right? To this, and this to this. So, and you go through everything, and then it will work. It will work. I to j, and j to I to k, and then k to j. Yeah, eventually it's the shortest path. It doesn't make sense. Right? You will have to go through, so you just find the shortest path from this to this, and this to this, right? I wonder if this order matters. If in my mind, I and j are the destinations, right? So node 0 and node 1, and I try all intermediates. And the intermediates we haven't found yet. How do you guarantee this will always work? In this case, you try this, and then you given one intermediate, and you go through all of them trying that intermediate, and then you go through all of them trying the other intermediate, right? And in my idea, we go through all of them, we go through all the intermediates for the first one. I think my idea doesn't work. Intermediate has to be on the outside. I think intermediate has to be on the outside. So once this is done, now we have the new ij, right? I have new ij using the given intermediate. Or it's the same. I is the intermediate, and no, add edge. So we add an edge, right? Or we just say if we add an edge, we will edge 0. That is interesting. To use this edge, because you add an edge, you want to use this edge. So the original, you have to go through one, and you go to another. That's interesting. All pairs of nodes update the entry by taking the minimum of its current value and the sum of I to from node to node. That's very interesting. Yeah. So if we call very few add edge, but a lot of shortest path, yeah, you should use this. Great. Yeah, that makes sense because you have to establish some ij value to begin with, right? And you can try some intermediate. Basically, you try some intermediate, and then you try some other intermediate. You try some other so the ij needs to set, and then the intermediate. Wait, hold a second. No, when you set intermediate on the outer loop, which means you have the same intermediate, and everybody's working around the same intermediate, and they're trying to say, okay, given this intermediate, what is the minimum that you can get? And the next round is given a different intermediate, what is the minimum you can get? So each time you have a different intermediate, and you are, because you're saying in the end, one of the intermediate will be the solution, will give you the minimum, right? One of them will give you the minimum. So you're just trying to find that one as you go through. Honestly, I don't know 100%, but I'm not gonna care. I think it's good to implement it. Never done what's it called? Floyd-Warshall. No, I think I've done Floyd-Warshall. I had a class in graph, but I don't remember it very well. Use the Floyd-Warshall algorithm according to the second official solution. All right, so for this we need this int adjacency list. We cannot do it here. So this dot, no, just adjacency list equals new int n for int I equal to 0, I smaller than n, I plus plus. For int j equal to 0, j smaller than n, j plus plus. We say adjacency list ij equal to integer dot max value, right? And then for int e, that's a good one, edges, adjacency list e0 e1 equal to e2. Right, this actually can be one line, and then we can actually say if, then we need this, unfortunately. Oh, yep, that's actually slower. So we do that, and for int I equal to 0, I smaller than n, I plus plus, adjacency list I equal to 0. Then use Floyd-Warshall to find the minimum paths, the minimum cost from I to j going through an intermediate k. So for int k equal to 0, k smaller than n, k plus plus. Okay. For int I equal to 0, I smaller than n, I plus plus. For int j equal to 0, j smaller than n, j plus plus. Oof. 3 levels. Okay. Then we say adjacency ij shall equal to math.minimum adjacency ij and adjacency ik plus adjacency kj. That's the key. So that's that. And add an edge, use Floyd-Warshall to update any edge, any I to j, update the distance, right? The distance of any node pairs, any node pair whose path cost can be reduced by including the newly added edge. So for int I0, I smaller n, I plus plus. For int j0, j smaller n, j plus plus. Then, oh, n. Then what? We say adjacency ij go to math.minimum adjacency ij adjacency I to edge 0 plus edge 2 plus adjacency edge 1 j. Right, so this is return adjacency node 1, node 2. So this, oh Lord, n squared. No, not squared. This is tripled. Right? This is O n squared. This is O1. Oh, so basically just swap where we do O1. That is not right. I know, because I shouldn't do that. 1E9. Incompatible types. Is that 1E9? Int. Oh. Because you have add. That's why. Oh, huh. Sorry, I forgot about this. Smaller than max, then adjacency node 1, node 2, otherwise -1. It's a good point. That was the example. That was the example. That's like Christmas tree. All right, that shall be it. All right, that'll be it. I like this one. It's first time really, I think last time I just didn't have enough Ghana to go through this to really understand what Warshall is. But I think this time is better. So Floyd-Warshall is to find the shortest path. And it's a different kind of way to do. I think overall, the actual is always faster, right? Because it's e log v. This is a v squared. No, v tripled, right? It's v tripled. So it's all depends. I mean, this question is all depend on how many times you'll call at edge and how many times you call shortest path. All right, that will be it for today.